Daniel is going to stay here, and he's joined by David Milward, CTO of Linguamatics. They're going to do a joint presentation on applying ChemAxon's naming technology in Linguamatics I2E text mining platform.
So I'm going to talk about some of the advances in this, the final year of the Chickle project. So this was a 2-year project sponsored by the European Union. And the aim of the project was to develop a chemically aware text mining system. And to do that, we've been combining the I2E, Linguamatics I2E interactive text mining platform with name-to-structure, substructure, and similarity searching from ChemAxon. So why are we interested in doing this? Well, text mining, and I'll say a little bit more about text mining in general in the next few slides, but in particular, when you're dealing with documents containing chemicals, you've often got things with patents, you've got a large number of different chemicals. Using text mining, we can actually filter to particular properties, particular roles of the chemicals in the documents. And we'll give plenty of examples of how we can do that and how we can pull out particular properties of the different chemicals within the documents. So I'll give a brief introduction to I2E's agile text mining approach, talk about the integration and processing of MOL files, and then I'll hand over to Daniel to talk about some of the evaluation work we've done during the project of name-to-structure. So what's agile text mining? Well, first of all, what's text mining, and how does it differ from search? Well, typically with search, you're taking a large set of documents, and you're trying to find the most relevant documents in that set to answer a particular query. In contrast, in text mining, you're analyzing the documents. You're trying to extract information by looking at the language in those documents. That can be purely statistics about the whole document corpus. It can be extracting facts and relationships, so individual little pieces of information from different documents, and then putting those together and summarizing them. So what it's giving you is a way to slice and dice the information. You're taking the unstructured data, you're getting structured results out, and then you can manipulate those results. So rather than getting back documents, you're getting back results which can more directly answer the questions that you have. So agile text mining is slightly different in that what it's trying to do is combine both the search and the text mining aspects so that users can ask arbitrary questions over arbitrary sets of documents. And since we introduced the I2E product, we've then seen quite a big expansion, especially in the pharma industry, where it's used by 9 of the top 10 pharmaceutical companies. And we've seen a big expansion in the way text mining is used. So 10 years ago, people were interested in protein-protein interactions and tended to think of text mining as a way of getting those and nothing else. Since then, people have been using for the vocabulary development, biomarkers, mining conference abstracts, competitive intelligence, going into marketing areas, looking at things like safety reports or SharePoint repositories. So a huge range of different applications are coming through because people can actually use the software themselves, try out new queries on new data sources. So how is it differing again from search? Well, one aspect is you've got a larger variety of ways of finding the information. So as well as looking with keywords, you've got terminologies. So you can search for the term cancer and not just get its synonyms, but all the different child terms, whether that's leukemia or lymphoma or astrocytoma. So in one search, you can often be picking up tens of thousands of equivalent keywords. You've got the language processing, which gives you precise linguistic relationships. And that can be useful both, and we'll see examples of how that extracts facts, finds directions of relationships. So a protein-protein interaction, you want the direction of that relationship, that protein A interacts with protein B and not, or phosphorylates protein B, not vice versa. It also gives you very localized negations, which are really useful for filtering. Things like regular expression search, so that you can actually, rather than looking for stemming, you can do more elaborate regular expressions to do more precise searches, for example, for microRNA forms. Chemical substructure, which we'll be talking about a lot here. And then high throughput, so where you're interested, for example, in saying, I want to find, are there any relationships to diseases for this 500 genes I've got from, say, a microarray experiment. So doing things in a kind of batch, high throughput way. So to give some examples, if we're looking at, say, using the linguistic patterns, you can actually use these also to find different ways of saying a particular concept. So if you've got something like risk factor for diabetes, if you just look for the string risk factor for diabetes, you'll find you'll get very few hits. You actually want to get all the kind of variation that's expressed here, and you can actually do that with very few linguistic patterns. So it's a more efficient way of doing things than if you were trying to look for individual strings. You can use the linguistics to make the generalizations. So this is an example for risk factors of diabetes, and we can then actually have a look and see the precise what are the risk factors for diabetes. So we can stick in a wildcard and then find all the different risk factors. Similarly, if we're doing something like Twitter, the language is more informal, but again, you can make generalizations. So here we're looking at different ways that people express getting a flu shot. And here we wanted to distinguish those people who are actually getting flu shots themselves versus people generally talking about flu shots. So we're also trying to get from the surface form to the semantics. So we're identifying the entities and relationships, whether we're finding chemical compounds, whether we're finding genes, or things or enzymes here linked to particular genes. We've got the particular gene IDs we're finding in the ontology. We've got relationships, such as relationship inhibits. Does this mouse actually connect? Actually, okay, I can use it. So we've got the relationship inhibits, but then we're using the linguistics to actually see that actually this is a particular grammatical construction. So we've got the COX-2 inhibitor, so that means that the drug is actually inhibiting COX-2 in this case. So then we can do a directed relationship between the two. So we can use the linguistics to actually take the little components of a sentence, which we've now given semantics to, and then put them together. Whether it was, in this case, drug, a gene inhibitor, or it could have been the other way around, something inhibits the gene. And once we've actually got things into a structured form, we can then present the results in different ways. And that means we can more efficiently get through a large set of different documents. So if we're interested in, say, genes and diseases, we might be able to get a summary of all the different genes. We'll find that some are very prominent. We've then got a long tail. We don't need to read all 470 documents about this particular gene. We can go down. We just need to look at one document, check the results are correct. Okay, so that's hopefully given some background of generally text mining and some of the uses in the life sciences. So now let's look at how we're integrating the chemistry into this. So first of all, we're integrating the named structure, and that means that we're getting the chemicals which are found by the systematic names as well as by the dictionary matching. We're then assigning, the named structure is then assigning those the structure, and we can represent that both as smiles or as inchi. We can output smiles or inchi, or we can output a preferred name. The preferred name is actually regenerated from the structure so that it's standardized. So we can have multiple different structures coming in. As if they've got the equivalent smiles, we'll give the same preferred name to them. So we use a common name if it's available, or a systematic name via the structure to name. So what that's allowing us to do is ask precise questions. So we might want to say what chemicals with this particular substructure act as inhibitors. Then we can look inside the text, find the particular compounds, find what we're inhibiting, find the particular genes, for example. So if we're interested perhaps in patent documents, we may be looking for a particular substructure. We're then finding the particular, in these cases, systematic names. They've been given a structure. We're now checking that that substructure is, structure is a substructure of the structure of the particular chemical. And in this case, we found, you can see the systematic names here found within the actual text. So this is a hit within the document. You could click through to see the actual position within the original document. And then we've found the structure, and then it's re-standardized the name according to the structure to name. So if we're interested, for example, for amounts, we can look for things like melting points or boiling points. We can look within the text for the melting point here. We found a particular amount here. And we're actually here looking at a particular region of text. We're looking for not just the melting point within the same sentence, but effectively here we're looking for it in the particular section talking about that particular exemplified compound. If we take our results into Excel, we can use sort of Excel as one of our output options. We can then use something like JChem for Excel to show the structures rather than the smile strings or the systematic names. So that gives us a way of then viewing the structures and the particular features, such as in this case the melting point and the value. So this is the equivalent results, but rather in a browser, you're now looking at it in Excel. We can also distinguish different roles of different chemicals. So for example, in this case, we're looking at the products of a reaction. So we're saying, if we're interested, rather than looking for all the chemicals in a particular patent, we can start subdividing them into the ones which have different roles. So whether the particular chemical is used as a solvent, whether it's used as a product of a reaction, we can subdivide them, so we can then focus on the ones which are of most interest. So here we were looking for particular linguistic constructions, things like giving an amount of a particular compound, to suggest that that's a product of a reaction. We can also do things like linking across a patent document. So if we, for example, in one part of a document have the exemplified compounds, we get the name from this part of the document. But later on, there may be a table of data within the document, and we can link between those two aspects. So in this case, we found the particular example 12 here. We found out what chemical is being mentioned. Then we found a table later on which says example 12 has an EC50 value of 8. And we can link the two together and create a new table which actually has the compound name in it, as well as the EC50 value. So that's useful as generally in patent documents, a lot of the interesting information is spread across the document. And you often want to limit yourself to particular compounds where you have some exemplified values. Okay, so I'll talk briefly about mol file processing. So a lot of the modern patents are associated with supplementary files. And so we're processing those, generating the SMARS and IUPAC names using the ChemAxon components. And then that means that we can actually link to the particular position within the document where the mol file was mentioned. So in this case, we're adding, when you view the document, we're adding in extra information, what the mol file ID was, what the SMARS was, and then we're generating a name from the mol file. And that means we can similarly connect together information from our mol files to particular information in proximity to those within the document. So there are some challenges in processing the mol files. You've got some very generic groups mentioned as mol files. You've got elided parts of structures. You've got parts of reaction mechanisms. There's also quite a big problem with people using the chemical editor as a general drawing package. And that's not always for chemistry. So in this example, this is actually a mol file here. So it's kind of this is not what you would expect to find in a mol file, but people have just used it as a general drawing package. So we need to remove those unusual structures to gain precision, so do quite a lot of filtering of the mol files. So once we've done that, we're then getting out the SMILE strings for the mol files. And similarly, we can look, for example, in this case, we've got mol files mentioned in tables. We're pulling out solubility percentages within that table. So again, we're connecting to the precise position of a mol file in the document so we can extract out information that's mentioned about the particular compounds. Okay, so I'll hand over now to Daniel to talk about the evaluation.
So one of the things, question we want to answer is, now that we are using name to structure to find the structures in the documents, how well are we doing this? Are we finding all of them? Are we converting to correct structure? So this is, until this project at ChemAxon, we were mostly testing a name to structure on names that were coming from databases, which is very practical way to test because you have the structure and the name, and you can check that you generate something which is either exactly the same or close enough, given that maybe the database is actually wrong. But in the wild and in this kind of project, you have more challenges, partly because you have a whole text, and so you can be confused about whether you have one chemical or several chemicals. You have, of course, OCR errors, line breaks, different formatting used by different people, and maybe unusual characters to encode different things like primes or brackets. One of the things we use to make this evaluation is existing gold standards. There's a manually annotated corpus of Medline abstracts, the Sky corpus. But we also wanted to develop our own gold standards, which we did both from Medline abstracts and from patents. And so we took random paragraphs from a patent, and we asked chemists to actually find, say that where are the names in this text. And there was, when you start to do this, there's quite a lot of work in the agreeing that what exactly do we want to annotate? Do we want to annotate the polymers or not? The chemical elements, the groups, so fragments of a structure. And so there is quite a lot of heavy work doing that. But so this was done. And so this is a graph of several corpus. And I must say that I got the feedback once that, oh, Daniel, you are again going to do a presentation at the UGM like you do every year. And every year you show us a graph of nicely going up numbers that are going up. And yes, it's, again, the time has come with a twist, as you will see. Now, if you look at these numbers, especially if you look in the middle at the Sky corpus, you will see that actually it started to go up, and then it went back to the level it started from, which is kind of disturbing. The reason for this is precisely that there are, for instance, in this corpus, there's lots of acronyms. So things like ATP, adenosine triphosphate, would be annotated as, yes, this is actually a chemical name. The problem is that sometimes the same acronym could be sometimes structure, sometimes not. And we have dictionaries that say that, yeah, this acronym can mean this, but it could mean something else. And so this is extremely difficult to actually do this correctly. And so what happened, if you see the green lines, this is 5.10, we decided to, by default, disable the conversion of acronyms in documents because it was giving too much false positives. And so in this specific evaluation, it made the numbers go down. But if you look at Medline, for instance, it's the middle. Yes, sorry, there is a missing legend, but the first column of these graphs is F-score, which is an average evaluation of whether this is good or not. But the second column is actually the precision, and the third is the recall. So you can see that with the green line in Medline, there's a big jump in precision because we stopped converting things that were actually not, we shouldn't have converted. But when we did that, we went down to another corpus. So it's kind of a hopeless situation. If you look at USPTO, it looks better because probably there are most cases you have systematic names. And so in this, we could improve. But so we felt that this method is a bit limited. It's useful and shows some improvement, and it was a driver to fix some issues or define. Once we added lots of options to say, do you want to convert the acronyms or not? Do you want to convert the fragments or not? Do you want to convert the chemical elements or not? So it made it possible to try to fit exactly the corpus, and it was useful. But so there's this problem with precision that it's quite hard to agree and to have good results. And the problem is that because this is manually done, it's actually a lot of work to get a relatively small amount of names. So in this corpus, we have, I think, a few hundred names. So it's useful to find some cases, but it's not really useful to drive improvement of the systematic algorithm. And so we wanted to have a larger evaluation set for the systematic names. And so we developed a novel approach, which actually David has this brilliant idea that in patents, very often you have a list of example 1, example 2, etc. And you can have 50 examples in the same patents. And using I2E, it's extremely simple to match this kind of paragraph, starting with example and then some text. And for instance, here there's 7 at the end. That's not part of the name. And so using this simple method, we could extract 70,000 names from 100,000 patents. So it's not that many. But it doesn't really matter. What we want is, it's still a lot. It's a lot of data, and you can see that those are really the kind of things we want to test on. So you can get automatically a very big list of things that actually appear in patterns. And so we can measure how well are we doing on this data, which is now much bigger than the previous one. This is a test set that's from the index of EPO patterns. And so because now it's a much larger set, we wanted to have at least a semi-automated method. So what we did is we took the openly available OPSIN software to convert those names to structures. And then it gives an indication about a possible structure for the name. OPSIN might be wrong, or it might not convert everything. But it's not just names. We have structures as well. And so here, what you see is among through the releases of the ChemAxon software, in blue, you see those cases where we generate exactly the same structure as OPSIN. And I must mention that we start at 3,000, so there are more. Obviously, there are lots of names which are not that hard, and so we can generate the correct structure without problem. In red, you have cases where we generate a structure which is not the same as OPSIN. And so potentially one of them is wrong, or maybe both of them are wrong. And in yellow, you have cases where we generated something and OPSIN didn't generate any structure. So here you can see quite clearly that things are getting better. In some releases, the focus is more on there's more blue. And so it means we have, well, if you have more yellow, now let's say, if the total is growing, it means we are converting more things. If the red is becoming smaller, it means that we are fixing some errors where we were generating the wrong structure. Many times it was the stereochemistry could be wrong, or other cases. But so you see that either one or the other or both improved in every release. And as a final test for the latest version, I show, for fairness, also what's the situation with OPSIN, the latest version 1.2. So obviously, this is compared to our latest development version. And obviously, the first two columns are the same, because those are the names where we agree or we agree to disagree. So we both convert it. And then, so in yellow, it means those cases that we convert and OPSIN doesn't. And in green, it's things that OPSIN converts and we don't. But so this was very useful to drive improvement, and it was good complementary to the manually annotated corpora. To go further, so there are still things in this set that we don't convert, and the question is how come? And so we identified several cases. There are cases in the red here that clearly it's not a name. So even though most of the things we pulled out of this query were correct or were really names, there was some cases where example pharmaceutical procedures, or I don't know. So it happened. So those, it's not something we want to, it's not a problem that we don't convert it. It's not a name. Then in blue, you have fragments. So it's things that we cannot convert it because it's not the complete name. It ends with a dash, and obviously something is coming later. And in yellow, it's things that probably most of them look like they could be converted. Most of them have OCR errors. And so I think so what you can know from this is that the recall what we had, so the red, it's not a problem that we didn't convert. So out of the rest, we converted 86% of this sample. It will obviously vary a lot. We'll do more on, for instance, USPTO or clean names. Now we do less because there are OCR errors. And out of the rest, so the 14% that we don't convert, it seems that about 1/3 is this blue case where it's a fragment. And I think it means that in many cases, for instance, what we saw is there are tables, and you can have a name which spans several lines of rows of the table. And so I think the blue cases is going to be work for you, David, and your company to pre-process these cases so that we can actually put them together to find the whole name. Bad news for me is that most of it is yellow. And so it means that in this case, it's the OCR correction mostly that will have to be improved. So the next steps in this collaboration between ChemAxon and Linguamatics So now we are, Linguamatics is working hard to release the first version of I2E, which will have the name to structure. And so they have an enterprise version, they have a hosted version. So they index the patent in on-demand version, so you can get access to the structures. They are converted from name to structure, from mole file conversion, and so you don't have to install it yourself. It's on demand. It's hosted, and you can do substructure and similarity search. And there is also, so maybe David, I hope I'm saying right, that there is a hosted version and there is a in-company version. So the next steps will be to integrate the chemical drawing in I2E, because at the moment, name to structure is there, but not from Marvin Sketch. And so if you want to make a query, you would have to paste a smile or a smarts. So they will integrate Marvin Sketch. And on our side, we will improve OCR correction and name to structure in general. And if you're interested in this collaboration in this project, then you can contact this email. You can see the Linguamatics stand, and Linguamatics will have their submit next month. So you can also choose to go there.
What are you going to do about materials that don't have smile strings? Because it looked like smile strings was the key intermediate in polymers and inorganics.
Yeah, actually, so if it got there, it means that somehow we understood something about it. So when it's not a smiles, it can be because we actually have in the dictionary, for instance, polymer representation. We have some representations in MRV. So in this case, you can actually store the name as a way to say this is the structure. So it's a actually very compact way, which is using the dictionary. So normally, if we could convert it, there is a way to represent it.
So you don't have to use the smile string.
Yeah.